Ever since I was a kid, I've been absolutely captivated by space. There's something magical about looking up at the night sky and wondering what's really out there. Today, I want to share with you how scientists actually study the cosmos, because it turns out understanding the universe is even more fascinating than I imagined. So let's start with the basics. You've probably heard of physics and astronomy, right? Physics is all about understanding how the natural world works. Gravity, energy, motion, all of that. Astronomy is the study of everything we see in the sky. But astrophysics? That's where things get really interesting. Astrophysics combines astronomical observations with physics to answer the big question, how does the universe actually work? Now here's the challenge astrophysicists face. Everything they study is literally out of this world. You can't just walk up to a star and take a sample. So they've developed three main approaches. First, observations using telescopes on Earth and in space. Second, laboratory experiments where they recreate cosmic conditions right here at home. And third, theoretical work using supercomputers to simulate everything from the birth of stars to the end of the universe itself. But let's talk about the most important tool in an astrophysicist's toolkit: light. And I don't just mean the light you see with your eyes. I'm talking about the entire electromagnetic spectrum. Here's something mind-blowing. What we can see with our eyes is just a tiny sliver of all the light that exists. The electromagnetic spectrum includes gamma rays, X-rays, ultraviolet light, visible light, infrared, microwaves, and radio waves. They're all the same thing, electromagnetic radiation, just at different wavelengths. Think of it like this. Wavelength determines everything. Gamma rays have the shortest wavelengths and pack the most energy. Radio waves have the longest wavelengths and carry the least energy. And visible light? We're sitting right in the middle, able to see wavelengths from violet, the shortest we can see, through green in the middle, all the way to red, the longest visible wavelength. That's why rainbows exist. Water droplets split white light into all these different wavelengths, revealing all the colors we can see. Now, light behaves in this beautifully strange way. It acts as both a wave and a particle. These particles are called photons, and they travel at, well, the speed of light. That's about 186,000 miles per second, or 300,000 kilometers per second. And here's the kicker. Nothing in the universe can go faster than that. It's a fundamental speed limit built into the fabric of reality. Why does any of this matter for studying space? Because different objects in the universe emit different types of radiation. Stars like our sun emit mostly visible light. But neutron stars? They're blasting out gamma rays, and most celestial objects emit multiple types of radiation at once. When astronomers observe the same object at different wavelengths, they're essentially seeing different aspects of it, like looking at something under different colored lights. Combining these views gives us incredible insights into how the cosmos operates. So let's take a tour of what's actually out there, starting close to home and working our way out. When you see a shooting star, you're watching a tiny speck of cosmic dust burning up in our atmosphere, maybe 60 miles up. If a bigger chunk makes it to the ground, that's a meteorite. Then there are satellites orbiting a few hundred or thousand miles up. Our moon sits about 239,000 miles away, close enough to look huge and bright in our sky. Beyond that, we have the planets of our solar system. And then, 93 million miles away, our sun, the closest star to Earth. That distance is so important in astronomy that we gave it a special name, 1 astronomical unit, or AU. But what about all those other stars in the night sky? They're just like our sun, only much, much farther away. The very closest star to us after the sun is Proxima Centauri, and it's 25 trillion miles away. Every single star you can see with your naked eye is part of our galaxy, the Milky Way, which contains hundreds of billions of stars. And here's where things get really wild. Because light has a speed limit, it takes time to reach us from distant objects. Light from Proxima Centauri takes 4.3 years to get here. That means when you look at it, you're seeing it as it was 4.3 years ago. That's why we measure cosmic distances in light years. The distance light travels in 1 year, about 5.9 trillion miles. Think about what this means. When we look at distant galaxies through our telescopes, we're seeing them as they were millions or even billions of years ago. We're literally looking back in time. Every photograph of a distant galaxy is a window into the ancient past of our universe. This is what I love most about astrophysics. It's not just about understanding what's out there, it's about understanding our cosmic story. By studying light from the farthest reaches of space, astrophysicists can peer all the way back to the beginning of time, to the Big Bang itself. They're solving a cosmic detective story, piecing together how everything, stars, galaxies, planets, and yes, even us, came to be. Because here's the beautiful truth. We're made of stardust. The atoms in your body were forged in the hearts of ancient stars. Understanding the universe isn't just about what's out there. It's about understanding where we came from and our place in this vast, amazing cosmos.
And that, to me, is absolutely worth looking up for.